All right, so in this video, we're going to talk about controller design, much in the same vein that I talked about observer design last video. So the general problem setup is given this system with where we have the aerodynamics and the state. So X is the state and E is the aerodynamics, where E is X minus the estimate of our system. and so we want to design K such that our system satisfies some characteristic equation. Okay, so again, the characteristic equation of our system is given by, again, it's let me get this up here, scroll down a little bit, zoom out, great. So the characteristic equation is alpha of S is equal to alpha naught plus alpha 1 S plus alpha 2 S squared plus delta Sn, and this guy is equal to 0. Okay, and so now this is representative of the eigenvalues of our system. So now we can choose the eigenvalues of our system. That gives us a characteristic equation, and then we can pick K such that the characteristic equation holds. And in general, we want that the first condition, there we go. First condition that we want satisfied is that the state E, the error between our estimator and our state, converges to 0 faster than X converges to 0. So what does this mean? This means that we converge to our estimate, that the estimate converges to the state faster than the state converges to the reference or the origin. So if we consider the case when the reference is equal to 0, then we get that our state has the following dynamics: A minus BK times X plus BK times E, right? So now if we plug in the aerodynamics, if we plug in the A minus BK into our characteristic equation, back up here, our characteristic equation, we can use again, Cayley-Hamilton theorem to prove that the matrix A minus BK has to satisfy its own characteristic equation. Okay, so this is the Cayley-Hamilton theorem. Implies that we get alpha of A minus BK is equal to alpha naught times I plus alpha 1 A minus BK plus alpha 2 A minus BK squared plus A minus BK n is equal to 0. All right. So again, just basically following the same steps as we did with the observer, we can look at the squares to evaluate the squares of each matrix. here. So let's look at a minus b squared. This is equal to a squared minus abk minus bka plus bk squared. And then this guy is equal to a squared minus abk minus bk on the left minus a minus bk. All right, so let's look at the cube. A minus bk cubed. This guy is equal to a minus bk times a minus squared times a minus bk. So that gives us a squared minus bk minus bk times a minus bk times a minus bk, right? And then if we do some manipulations, this will result in a cubed minus a squared bk minus a bk, a minus bk, minus a minus bk times a minus bk. So if we do this out a couple times, oops, let's see that goes there. So we do this out a couple times, we can see a pattern here. I don't know if you guys can hear the squeaking, but he's got a toy that he loves. And even though he's laying down, he has to chew it. All right, moving on. All right, so if we do this out a couple times, we'll notice that if we go to the nth power of a minus bk, this results in a to the n minus a to the n minus 1 times bk minus a to the n minus 2 times bk times a minus bk minus out to bk a to the n minus bk n minus 1. Okay. So then we can do a similar factorization like we did for the observer design. And then this leads to the following. We get, so after some manipulation, we get the following expression. We get that alpha a minus bk, so the characteristic equation is equal to the characteristic equation of a minus the controllability matrix times this matrix J, and which is equal to 0, where J, let's go to the next page here, maybe. Wait. Where J is equal to alpha 1 k plus alpha 2 k a minus bk plus all the way out. We get alpha 2k plus alpha 3 k a minus bk plus all the way out. And then this goes down to just k. All right, and so then, since we're just interested in the value k, this is what we want to find. Since interested in finding k, we can multiply to the left by a matrix similar to the observer Ackermann's formula. 0, and then have a 1 on the very last entry, times the controllability matrix C inverted, times alpha of A. All right. And so this is called Ackermann's formula for the state for the controller. Ackermann's controller formula. Come on. Again, there's a couple caveats. One is the eigenvalues. Of A minus BK and A must be disjoint, so they can't coincide. And two, the system must be controllable. So it's nice because we can use the controllability matrix first to decide if it's controllable or not, and then we can use the same controllability matrix to actually design K and find out what K we should use given right. Awesome. Yeah, that's all I have.